Okay, so we're going to look at ANOVA here, and this is a particular ANOVA in which we've got more than one independent variable. T-tests and non-parametric equivalents are fine if you're looking at differences between means where there's only two means, two conditions, looking at whether A is bigger than B. But once you've got more than that, then you have to do analysis of variance so long as your data permit it. There are non-parametric equivalents of ANOVA, which we'll look at somewhere else. So what we've got here, I mean, there's nothing on the screen at the moment, but I want to just give you a little bit of a heads up about setting up data when you do an ANOVA. What we've got here, the data that we're going to look at is, the outcome is how many hours of therapy a particular person needed to have in order to be well, or in order to meet some kind of criterion. And our independent variables, that's our DV, our independent variables are the kind of therapy that we have, so whether it's cognitive therapy or person-centered therapy, and the other independent variable is gender, so male versus female. So what we have there is what's sometimes called a 2x2 design. We have two levels, and each level, two variables, two independent variables, and each independent variable has two levels, so 2x2. You can imagine that as being like a little table in which you've got four sections, four squares, and each one of those boxes represents the score in a variable, or a mean. So we basically have four possible conditions, 2x2. 2 times 2 is 4. Now the reason why I want to step you through the setting up of this is that sometimes you can unfortunately think in terms of conditions rather than in terms of variables, and this really kind of messes things up. And just to give you an idea that how tricky SPSS can sometimes be, 3 weeks ago I was doing a lab class with some undergraduate students, and I decided to set the data up. They were shouting the data out and I set it up, and I knew that this was a 2x3 design, so two variables, one with two levels, two variables, one with two levels, one with three levels, which gives 6 conditions. 2 times 3 is 6. And rather than think in terms of variables, I just set them up in terms of conditions. So I had one single column which had all 6 of the conditions. So I used 6 coding variables. Condition 1, condition 2, condition 3, condition 4, condition 5, condition 6. Completely wrong, because I couldn't do the analysis. So it really helps to begin with if you're thinking, okay, this is a between participants design that we're doing here, as was that. Think how many variables do we have, and what are those variables? That's where you've got to think. So the first thing you ask when you look at a problem, a statistics problem, is, what kind of design is it? Is it between design, where everybody gets a different condition? Is it a within design, where everybody has the same treatment condition? Or is it a mixed design, which we'll look at later? And in a mixed design, you have a combination of between and within subject variables. First thing you ask is that. This is completely between, so we know that what we've got to do here is have coding variables. So we have one column, which will be our outcome measure, and then think we have two variables, sex and the type of therapy. So let's go into variable view, and first, well, let's just call the first variable therapy. That's our variable, and we need to set up a coding variable in here so that one is cognitive. I'll be quite brief with this, and then the other one is person-centered therapy. Just call it PCT. Remember, you have to click add before it'll do anything. If you just click OK now, it'll abandon it and won't make the changes. So that's our first one. The second variable is sex or gender, and obviously that is, let's use 1 for female, and we click add, and we click 2 for male, and we click add, and then OK. And then our final variable is hours of therapy. And we don't need a coding variable for that because it's a simple continuous variable. It's a ratio scale because it has a true zero. If no hours of therapy, it literally means no hours of therapy. So it's a ratio scale. So we go back to our data view now, and we can see that we've got the various things here. This little magic button here, which I really like, where we click on this label here with the A and 1. We can type our numbers in here, and magically the variable names will appear like that, and the same with sex. And don't type 22. Make sure you type the numbers correctly. We've had kind of somebody last week where a participant scored 19 out of 10. It's very easy to make mistakes, so it's worth, I would say, particularly if your life depends upon it, or at least your project mark depends upon it, it's worth, before you even do the analysis, going through the data, making sure you've got everything right, all the variables are right, and all the data, the actual dependent variables are correct too, before you actually do it. Because there's nothing more depressing than finding you've got a lovely significant result and then realising that's because you typed the numbers in wrong. Don't do that. So I'm not going to type any of the numbers in here. I think I've said enough about that, so let's close this window down and go to the data here. So we can see the exact same thing. Gender, I've got it the other way around, we've got cognitive therapy, and we've got the number of hours. Now, important thing to remember here, more means worse. The more session hours it takes you to reach a particular level of functioning or a criterion in terms of your mental health well-being, the more hours it takes, you think the worse the therapy is because it's taking longer. So short means good, small numbers mean good. Okay, so we've got the data set up here now. Now, what you should do at this point, of course, is to do all your tests for normality, etc. I would recommend that at this point, once you've got the data, and the first thing you do is check for outliers. Check for outliers, do a box plot. There's another screencast on that. If you've got any kind of dots which look a bit troubling in the box plot, then convert them to Z-scores and check to see whether any of these are potentially problematic. If they are, deal with them. Again, more information on that particular screencast. Once you've done the box plot, then I would do the test for normality. So you can do that either via frequencies, or you can do it via the analyze function in here, and you can go explore, and that will also allow you to determine whether your data is skewed. If you sorted the outlines out and the data are fine, no skews, then it's permissible to start doing the ANOVA, so long, obviously, as your dependent variable is interval or ratio. Okay, this all is, everything's fine, I've done that, so let's get on with it. But do that first before you even look at the means. Remember, a mean doesn't mean that much if the data are skewed, because outliers and high extreme scores have the property of turning the mean into an unrepresentative statistic. It doesn't represent the typical person. So before you do anything, descriptives and inferentials, check for outliers and check for skewness. And I suggest checking for outliers first, because sometimes an outlier can cause skewness. In other words, somebody's got such an extreme score that it's dragging the distribution into being positive or negatively skewed. So it might be that it looks skewed, but if you simply deal with the outlier, then the skewness may go away. If you've dealt with all the outliers and it's still skewed, then there are various things you might do, including using non-parametric tests or using a transform, and I think I discussed that in the lecture, where you basically do a log or reciprocal transform of the dependent variable to try and get rid of the skewness. More on that anyway. Let's get down to ANOVA. Come on, let's get into this. This is good. So, ANOVA, what do we do? Well, a number of different ways of doing a one-way ANOVA, where you've simply got one independent variable which has got more than two levels. That's the kind of one you did in the lab class. But let's have a look at this. Where do we go? Okay, rather helpfully, SPSS has given it an extremely intuitive name, where the ANOVAs are all hidden under a thing called general linear models. Of course they are, that's where they are, because we all know what that means. Rather than calling them ANOVAs, which is what they all are, we kind of obscure it to make life difficult. Not generalized linear models, which is something completely different, general linear models. Now you might be seduced when you look at this thinking, oh, we've got two IVs, therefore we're doing multivariate ANOVA. No, we're not, actually. It's univariate, paradoxically, but univariate because what we're talking about here when we're talking about variable, the variate part of it, is the dependent variable. So uni means one, but what we're talking about here is not the IVs, it's the number of DVs. So univariate it is. Again, obvious and transparent from SPSS there. So we want to do a univariate analysis of variance. Multivariate, as I might have already suggested, is where you have more than one dependent variable. That's kind of like a MANOVA. That gets very complicated. More of that in a different module. So let's click on that and see what happens. Oh, that's clear. I've been practicing here before. So we've got three little things in this box on the left here, and the first thing is find our dependent variable. Dependent variable, what is supposed to depend on what? Well, we would hope that the number of session hours depends upon, for example, the therapy that a person has been given. We wouldn't expect to think that the kind of a therapy that somebody had been given depended on how many session hours they had. That'd be ridiculous. So that's our DV. And then our fixed factors, again, SPSS being helpful there, are our independent variables. So we put those in there. And unlike with the t-test, you don't need to tell it how many levels there are. That's all done for you. Leave all these alone. We don't need to know about random factors, covariates, etc. at the moment. But what we would like to do is, first of all, and I think this is really, really important and not to be overlooked, is get some graphs. So here are some plots, and what we can ask it to do gender on a horizontal axis and have therapy as separate lines. And again, a bit like doing coding variables, you then click add. And then what I suggest we do is do it the other way around, because sometimes, I didn't nearly click continue without clicking add. Do it the other way around, because sometimes if you've got a graph, so one graph can often make more sense than another. So if you ask for both, then it will give you two graphs and you can look at them and see which is most intuitive and makes more sense to you. You can't often predict which is going to be the most sensible one, so I just say get as many plots as you can. Really, really can't emphasize enough how important it is, particularly once you start getting to ANOVAs and more complicated designs and analyses like this. Can't say how important it is to really look at graphs. If you've got two means, you've done a t-test, that's bigger than that. That's easy. You don't need a graph. Once you've got two variables, trying to get your head into what's going on by looking at the numbers is quite tricky. So I think get plots, and before you actually even look at your ANOVA table, have a look at the plots and try and see what's going on. Let's click continue, and then what we might want to do now is to get some options. We can get descriptive statistics if you want. I mean, this is the nice way of getting them, so we can display means for gender and therapy. Ask for some descriptive statistics there. We want to get estimates of effect size to know how big these effects are, as well as if they're significant, and homogeneity tests. A bit like t-test, one of the things that ANOVA is fussy about is that the variance of the scores is approximately the same for each of the conditions. If one of the conditions has got a lot of variation in it, a lot of dispersion, a high standard deviation, a high variance, then it really kind of contravenes the assumptions on which ANOVA is based, and you really have to do a correction, just in the same way that you do with the t-test. Remember Levine's test for the quality of variances, same kind of thing as that. So we need to know that, to know whether our ANOVA needs to be tweaked or anything like that. And let's just click continue, and then let's click OK. So let's not look at any of the numbers first. Let's just look at the graphs. What seems to be going on here, you might ask? Well, what we've got here is, it seems that cognitive therapy, if you're a female, is not very good. Remember, a big score is how many sessions you did, which is suggestive that this is not a very efficient therapy. But on the other hand, if you're a male, CBT seems to be very good, or at least better than if you were a male and using person-centered therapy. So person-centered therapy for females seems to be good, but cognitive behavioural therapy for females, which is in fact, let's look at a different graph, which uses females as the lines. This is why I said that some of the graphs make more sense than others. Same graph, just the other way around. So for females, this is comparing females. PCT is good, but cognitive behavioural therapy is not so good. For males, which is the green line here, cognitive behavioural therapy is good because it's fewer sessions, whereas person-centered therapy is less good. Now, unfortunately, I'm going to have to click on this and do another screencast of this, so we're going to have to go for part 2 because I'm nearly up to 15 minutes, which is the maximum number of minutes that you're permitted. So let's stop.